All right, welcome back. We're here in section 12.3. We'll divide this up into three parts, and we're going to be looking at inference for slope. Slope is what we're looking at. So once again, we'll kind of go through some learning targets here, and these are the things that we should be focusing on. All right, so scatter plot of the duration of interval between eruptions of Old Faithful, the Olio Geyser, for 263 eruptions in a single month. The population least squares regression line is shown in blue, so we can kind of see the pattern that's formed there. Some interesting data there. All right, so now a regression line calculated from every value of the population is called a population regression line, or we say it's the true regression line. And the equation, we use the symbols here with the mu sub y is equal to alpha plus beta x, where this is the mean y value for a given x value. This is the population y-intercept, and of course we have the population slope. Now, a regression line calculated from a sample is called a sample regression line, obviously, or estimated regression line. The equation of that sample regression line, we have the y-hat is a plus bx with those variables there. Okay, so here are scatter plots of least squares regression lines in green for three different simple random samples of 15 Old Faithful eruptions, along with the population regression line in blue. And as you might guess, here are the different samples. We can see some different things where those slopes of those sample lines are certainly different. So different than that population. So, we had slopes of 10, 12.5, and 15.7, with the actual population slope being through 13.29. So that's kind of done by its sampling distribution. So the figure here that we see down below now shows a dot plot for the sample slope of the least squares regression line in 1,000 simulated simple random samples of 15 eruptions. And so we have our population. Blue vertical line is the population slope, what we have there. So as you could probably guess, some things that we're seeing here is that the shape is that it's approximately normal. The center is that population slope, which is an unbiased estimator. And we have the variability here. So we have a standard deviation here of about 1.42. And that's the standard deviation for the 263 eruptions that we had. Okay, so what we're going to do, if we choose a simple random sample of n observations of x and y from a population size n, we know then that the mean of the sampling distribution of B is a beta there. The standard deviation of the sampling distribution of B can be found by taking the standard deviation divided by the sample standard deviation times the square root of the sample size. And so the sampling distribution should be approximately normal. And again, B is the slope, remember that, as we were talking about that. All right, so now when the conditions for inference are met, the regression model looks like the one shown here. The line is the population regression line, which shows how the mean response of mu sub y changes as the explanatory variable x changes. Now, for any fixed value of x, the observed response y varies according to a normal distribution having mean mu sub y and standard deviation sigma. And we can kind of see that graph that we see there. All right, so here are our conditions. And we're going to kind of remember it as liner. Liner is what we're going to remember it as. It's got to be linear, all right, independent, right? And then without replacement, also check the 10% condition. We've done that many times. Normal, make sure that it is a normal distribution and that we also have equal standard deviations. It should be the same for all those x values. And then it should be random, comes from a random sample. So as we kind of look at it, as we use the acronym liner, yeah, that's what we're going to be checking for. Those are the conditions that we're going to be checking for on those. And here's kind of a summary of how to check those conditions. So to make sure it's linear, examine the scatter plot to see if the overall pattern is roughly linear, and I think this one shows it. But just make sure there's no leftover curve patterns if we do the residual plot. Yeah, we don't want to see anything that's left over that's kind of curved as we go, and that one is, so that's a bad one. If we see that, so we don't want to see that. Independent, okay, knowing the value of the response variable for one individual shouldn't help predict the value of the response variable for others. And then again, if we're not doing replacement, make sure that we're doing our 10% condition. To check if it's normal, make a histogram, dot plot, stem plot, box plot, normal probability plot of the residuals. Check for strong skewness or outliers. We'd like to kind of check that. So again, check to make sure that it's normal. Make sure we have equal standard deviations. So as we kind of going here, yeah, we're kind of seeing that residual roughly, yeah, all x's kind of have those same variabilities. Where here you can see the variability is getting stronger as the x value is getting bigger. So yeah, that'd be an example of something that's not a good one. All right, and then random, make sure it came from a random sample from the population. If not, you can't really make inferences. Okay, so make sure it's random. All right, so there we are, the Liner conditions. So let's see if we can do that here. Mrs. Barrett's class did a fun experiment using paper helicopters. After making 70 helicopters using the same template, students randomly picked 14 of them to each of 5 drop heights. So we had 152, 203, 254, 307, 442. Teams of student released the 70 helicopters in a random order and measured the flight in times and seconds. Now, the class used computer software to carry out a least squares regression analysis for these data. Here are a scatter plot, residual plot, and the histogram. So let's check those conditions and see what we have here. All right, so for the first one, is it linear? I mean, yeah, the scatter plot kind of shows a linear pattern. I would say so. No leftover curves in the residual plot. It kind of looks like they were released in a random order, so no helicopter was used twice. Yeah, results of 1 shouldn't be. So I think that's independent. Looking at normal, looking at that histogram, I definitely would say that it looks normal and no strong skewness or outliers. Equal standard deviations, it kind of looks that way as far as the scatter about the residual. It seems like it varies a little more when you're at the 307, but I think everything else looks pretty good in that regard. And then, of course, random. Yes, we were randomly assigned to the 5 possible drop heights. And then, so remember, Liner, that's what we're looking for. Those are the conditions that we're kind of looking into. Okay? All right. And then, so just remember, don't overreact to minor issues in the graphs when checking normal. It's got to be strong, and it's got to be really kind of blatant. So don't overreact to those types of things. All right, so that takes us through the first part. We'll go 3 parts in section 12.3. There's some nice problems on page 831. Check out 65, 67, and 69. That'll help us make sure we're ready to move on till tomorrow when we do 12.2. Until next time, I am Mr. Boone.